Hello friends, welcome to our channel HT and LT Electrical and Electronics Engineering. In the previous video, in the current transformer part 1, I discussed about current ratio error and phase angle error. What is current ratio error and phase angle error? Here it is current transformer part 2. Let's start. Some of the terms frequently come across in connection with the current transformers are defined as below. Ratio error is the percentage error in magnitude of secondary current given by the formula KT IS minus IP divided by IP into 100. KT is the rated transformation ratio, IS the actual secondary current when IP primary current is flowing in the primary winding. IP the actual primary current. Phase displacement. Phase displacement is the difference in phase between the primary current IP and the reverse secondary current KTIS. The direction of the vectors so chosen that the angle is 0 for a perfect transformer. The phase displacement is said to be positive when the secondary current vector leads the primary current vector. It is usually expressed in minutes. VA burden of a current transformer CT is the maximum load that can be applied to its secondary, measured in volt amperes or VA. This may be up to 30 VA. The burden can also be expressed as the total impedance in ohms of the circuit. To calculate total burden of CT, the burden of the instrument, ammeter or kilowatt hour meter, function meter, coil, instrument coil and wire are measured separately and added together, and the result is then multiplied by a safety factor of 1.2 or 1.5. Here is different meter, analog meter, digital meter. Here is the burden of the meters. Analog meter burden 1 VA, digital meter burden 0.5 VA. Current coil of watt meter, VAR meter 1.5 VA. Current coil of energy meter 2 VA. Current coil of PF power factor meter 2.5 VA. Current coil of tri-vector meter 5 VA. Okay, next. Composite error. The composite error takes into account both the ratio and phase angle errors of the CT and is expressed as a percentage of the rated primary current. The composite error of the measuring current transformer is equal to or greater than 10% in order to protect the apparatus supplied by the current transformer against the high currents produced in the event of system fault. Composite error is the RMS value of the difference under steady state condition integrated over one cycle between A, the product of the rated transformation ratio and the instantaneous value of the secondary current and instantaneous value of the primary current. This is generally expressed as a percentage of the RMS value of primary current according to the following expression. Here is the composite error expression. In KTIS minus IP whole square integrated over 0 to t time and divided by 1 by t and root over, and it is the percent expressed as a percentage of RMS value of primary current. It is composite error. Accuracy limit factor. The accuracy limit factor ALF of a current transformer is the primary current value at which the CT meets the composite error requirement. For protection current transformer, the ratio of the accuracy limit primary current to the rated primary current is called ALF. For protection current transformer, the ratio of accuracy limit primary current to the rated primary current is called ALF. In other words, this is the maximum value of primary current beyond which the core of the protection CT starts saturated. CT secondary current. Whatever may be the CT primary current, CT secondary current is always 5 ampere or 1 ampere. When the distance of CT is far from relay and panel board, secondary current 1 ampere is chosen. As an example, outdoor substation. When the distance of CT is near to the relay inside the panel, secondary current 5 ampere is chosen. As an example, indoor substation. Okay, next. Knee point voltage of current transformer. It is the sinusoidal voltage of rated frequency applied to the secondary terminals of the current transformer, all other windings being open circuited. Means primary side will be open circuited. When being open circuited, when increased by 10% of the rated voltage, causes the exciting current to increase by 50%. Here V is the secondary voltage and IE is the exciting current, secondary exciting current. When it is increased 10%, the secondary current IE also increased 50%. There is the saturated region. A is the angle point at the start of the graph is used for metering coil in CT. K is a knee point, a point where the excitation current starts increasing beyond its limits. In the next page, it will be explained more details. Okay, next. Typical arrangement of knee point voltage determination of current transformer. Here it is 220 volt 50 amp supply. Here is a switch and here is a variac. Here it is the current transformer and here it is a step up transformer 0.22 by 6.6 kV step up transformer, and here again step down potential transformer to measure the voltage 6.6 kV 0.1 kV potential transformer to measure the voltage by voltmeter, and here is ammeter secondary side, and here is the primary side P1 P2 S1 S2 current transformer. Typical arrangement of knee point voltage determination of current transformer. When a voltage V is applied to the high voltage secondary side of a CT with primary open circuited condition, then self-induced EMF E is produced, which is called back EMF or counter EMF, which is in opposition to V. When V is gradually increased step by step, E is also increased gradually. E is almost equal to V. Only exciting current IE is flowed up to saturation level. When saturation level occurred, then V is greater than E. IE started to increase significantly due to lack of production of E. The voltage where 10% increased at the voltage where 10% increased in rated voltage, the IE increased 50% is called knee point voltage. In other words, knee point voltage is the voltage when saturation of the core started. Okay, next. As per operation, current transformer are three types in general: instrument current transformer, protective current transformer, PS class current transformer. Instrument current transformer. Here is the ratio characteristics of an ideal instrument current transformer. Here is the I secondary, here is I primary. IP is the rated primary current, here is IP, and IS rated secondary current. Ratio characteristic of ideal instrument current transformer. The excitation curve of instrument transformer must be a straight line up to say 125%, 125% or 150% of rated current. Beyond this, the value is not only immaterial but rather desirable that the core saturates so that in the event of faults, when heavy fault current flow in the primary of the cities, the connected instruments current coil connected in secondary will not burnt out. An ideal instrument transformer should therefore have the characteristics as shown in figure. Okay, next. As would be seen, even with high primary overcurrent, secondary current exceeds the rated secondary current IS by only a small amount. As would be seen, even with high primary overcurrent, secondary current exceeds the rated secondary current is by only a small amount. This protects the instruments from the effect of fault current. The core of the instrument current transformer is made of nickel iron alloy or high permeability. The instrument current transformer are classified according to ratio errors are 0.1, 0.2, 0.5 and 1 classes, which means value of current errors are as follows: plus minus 0.1%, plus minus 0.2%, plus minus 0.5% and plus minus 1%, and the upper limit of phase displacement as follows: plus minus 5, plus minus 10, plus minus 15 and plus minus 30 minutes. Another two classes of CT are 2 and 3 of current error of 3% and 5%. Protection current transformer. Now it is protection current transformer. Ratio characteristics of ideal protective current transformer. When IP is rated primary current, IS rated secondary current. When IP is 20 times and IS also 20 times. Okay, next. It is not required for the protection current transformer to maintain great precision over the normal operating range. Rather, it should maintain the current error and phase difference within reasonable limits in the fault current range. It is necessary that the protective current transformer does not saturate up to the values of the current necessary to operate the relays. The current ratio characteristics of such a current transformer should be identical as shown in previous figure. The core of the protection current transformer is made of grain-oriented silicon steel of low permeability. The protective current transformer are classified according to current error plus phase error are 5P10, 5P10, 10P10, 15P10, which means that the upper limit of current error and phase error of the protective CT as follows: 5%, 10%, 15%, up to 10 times the rated primary current. If it is said 5P20 is an accuracy specification for protective current transformer, that indicates it can handle up to 20 times the rated primary current with an error of less than 5%. The conventional protection CT is used for overcurrent earth fault short circuit protection. Okay. PS class CT. PS class CT, it is a special class protection transformer which is mainly used for unit protection scheme or internal protection scheme such as restricted earth fault protection, differential protection used for transformer, generator. A PS class CT is defined by not only its accuracy at ALF, rather by its knee point voltage. PS class CT is defined by the knee point voltage. This is very important as the CT must not saturate under external fault condition. Here is a differential protection. Here is the winding. This is protected by two CTs, identical CTs, CT1, CT2. CT1, CT2. This is called differential protection. Here it is the relay. The two current is in secondary current I1 and I2 is in opposite direction. Note, when secondary current of CT1 and CT1 and CT2 is same, I1 minus I2 is equal to I1 minus I2 is equal to 0, the relay will not trip. The relay will not operate. But when there is I1 unequal to I2, the relay will trip. Suppose we use here conventional protection transformer 5P10 for CT1 and CT2 for differential protection scheme. Now an external fault occurs 20 times the rated primary current. Then our CT will give accuracy up to 10 times the fault current. Now an external fault occurs 20 times the rated primary current when our CT will give accuracy up to 10 times the fault current. When 20 times the fault current flow, one CT may get saturated and other not. One CT may get saturated and other not. Which one is saturated will give 0 secondary current. Thus there is a current difference will occurs between incoming and outgoing sides. Which leads to a nonsense tripping in the system. To avoid these types of nonsense tripping, instead of generalizing on the minimum saturation level of the CT, the user have to exactly specify the saturation level of the CT. This is called knee point voltage. Okay, next. The minimum knee point voltage for a given PS class city is calculated by VKP is equal to K into IFS into RCT plus RR plus 2RL, where IFS is the maximum through fault current as reflected at CT secondary is equal to IFP divided by CT ratio. RCT is the CT secondary winding resistance, RR relay impedance in ohms, RL maximum one way lead resistance from current transformer to relay, K factor of safety normally taken as 2, which means that for 2 times the maximum possible fault current the CT will not saturate. Both the incoming and outgoing CT characteristics would exactly coincide, that is their secondary current would match exactly and the scheme would not operate for any external fault. The general specification of PS class CT are rated primary current, turns ratio, knee voltage, exciting current at knee voltage and secondary winding resistance. Okay, thank you for watching the video. If you think the video is useful to you, then please subscribe our channel and share it to your friends. We will meet in the next video of CT part 3. There I discussed about the construction and some application of CT. Okay, thank you. Bye.